Okay, so first of all, let me call your attention, especially to those of you that have the PowerPoint slides printed out. There are 2 slides before this one that have more ice table practice problems. Okay, let me just show you. I mean, there's 2 problems here that we did not do last class. You are welcome to do them if you want more practice. I have the answers if you want to check it. Okay, but this is where we're going to start today. And I love this problem because it brings together 3 topics into one problem. It's got equilibrium, gas laws, and stoichiometry all in one place. Sounds like a great time to me. And actually, it's not even a very difficult problem, but I'm going to give you some time to work through it. I just want to kind of set it up for you. Okay? I'm always trying to model for you the best way to tackle a word problem where you've got numbers all over the place. So it says, for the reaction below, Kp, stop there. What does P stand for? Pressure. Pressure. Thank you. Kp equals 1.16 atm at 800 degrees, and we're given a reaction. What's the first thing you do when you see a reaction? Make sure it's balanced. It is. Okay, great. Before we read the rest of this, let's focus right here. Kp. If you would, please, tell me, for this reaction written in yellow, what would the Kp expression look like? Remember, expression means no numbers, no math yet. Okay? What would it look like? Tell me.
The pressure of carbon dioxide.
Okay, so he says it would look like this. I thought K was, products over reactants. Where's the over-reactants part? Tell me. Okay, it's the only gas. Remember, Kp applies to gases only. Let's just review for a second. What if that said Kc? Doesn't really change the problem, but Kc applies to what states of matter? Gas and aqueous. Okay, good. And they've given us a number for this. So all that has happened here, guys, is basically they've given us a sneaky way of telling us what the pressure of carbon dioxide is. Okay? That's all they've done there. All right, so I have the pressure of CO2. Let's continue. If a 20-gram sample of calcium carbonate, I'm going to write that in, is put into a 10-liter flask, I'm going to just put a V because that's the volume, heated to 800 degrees, that's the temperature, what mass of calcium carbonate will be left in the container? Okay, well, think about this for a second. I have information about this product, and I'm being asked a question about this reactant. I'm asked about something here. Does that look like a stoichiometry situation? Yes, it does. But it's also got gas laws stuff in it. Go back to the gas laws chapter. What is the one question you should ask yourself when you've got a gas laws stoichiometry situation? What's the question? Yeah. Is it at STP? Is it? No. Do you remember, if it's not at STP, what must you use at some point? Okay, PV equals nRT. I'm just going to write it up here. Okay. Now, just to make sure, because I don't want you to make this error, what's the name of this equation? What's it called? Thank you. The ideal gas law. Don't you dare try to plug in something associated with the solid into the ideal gas law. Here's where I would start, and you take it from there. You know you're going to use this equation. What I would do is look at each variable and ask yourself, do I have these things? Do I have pressure? Do I have volume for the gas? Put check marks above each variable. See what you're missing and start there. Go. All right, ladies and gentlemen, check your answer. Let me just point something out, because as I was walking around, I saw a handful of people doing something, and I just want to make sure you understand why what I saw people doing is not correct. What I saw some people doing was using the 20 grams of calcium carbonate that we were given, using that number, and doing stoichiometry with it. Here's why you can't do that. Okay, well, for two reasons. Number one, the end of the problem, the last phrase, says what mass of calcium carbonate will be left in the container, which implies that not all 20 grams was consumed, okay? Meaning there is some left over. So you can't use this. That would be like using the amount of an excess reactant to solve for how much product was made. So if you had done that, you'd get a wrong answer. Also, you don't need to convert grams of calcium carbonate to carbon dioxide because you already had a way to find out how much carbon dioxide was created. Okay? So just be careful and make sure you read these problems carefully. Okay, so let's move on, and this is our last topic for this chapter, Le Chatelier's principle, which you definitely did in Chem 1, and let's just review what it means. So Le Chatelier's principle says if you have a reaction that is at equilibrium, okay, it's like in its happy place. If you come along and mess up that equilibrium system somehow, that obviously it will no longer be at equilibrium, but it will eventually get back to it. And the way that it will get back to it is by shifting either to the right or the left. Okay, so there's three ways that you can mess up some equilibrium. And the first way is by changing the concentration. And let's look at an example. Another way to think about how you change concentration, you could also say, changing the amounts. So let's look at this example. And let's say, this is at equilibrium. That's what that double-headed arrow means. And let's say to this system, I add more of this reactant. That's going to cause a shift. Now, in which direction is it going to shift? By either reading this statement or remembering from Chem 1. Which way is it going to shift? Correct. It's going to shift to the right. It says things will shift away from any added component. Okay. Let's say I do this. This time I take out some of my product there. which way is this going to shift? Also to the right. Okay, because as it says, if you remove something, the reaction will shift toward it. Okay? Let's just try one more, just to make sure that you've got this. What happens if I add more solid carbon? What's going to happen? It will not shift to the right. It will not shift to the left. There will be no shift, no effect. Anybody want to guess why? Correct. You've got to pay attention. Okay? No shift, no effect. Because of this. You've got to be careful. Pay attention to your states of matter. Let's review for a second. Kc, what are the states of matter that are included in a Kc expression? Right, gases and aqueous. So ladies and gentlemen, a solid or a liquid is not going to affect your equilibrium. So your answer in that case would be no shift, no effect. Okay, so changing the concentration is one way of affecting a system. Here's another. Changing the temperature. Okay, now this one is kind of special because you can't answer a Le Chatelier's question where you're changing the temperature unless you are given one additional piece of information. And that additional piece of information is whether the reaction is endo or exothermic. And I realize we haven't talked about that yet in here. In fact, that is what our next chapter will be on, thermochemistry. Okay, but you should have heard these terms in Chem 1, so let's just review that. All right, we'll start with endothermic. First of all, as I said, I have to tell you whether a reaction is endo or exothermic, and I could do that in one of three ways. I could either say the following reaction is endothermic, pretty clear. Another way I might tell you is by giving you a delta H value. Okay, that's something called enthalpy. Don't worry about that word right now. But the point is, if this value is positive, that indicates endothermic. Okay, we'll talk next chapter about why it's positive. Okay, but there's a third way. Now, think about it. An endothermic reaction means heat energy is required. Heat or energy is absorbed. So if I was going to write the word heat or energy into this equation, does heat absorbed, heat required, does that sound more like heat is a reactant or a product? Right. It's more like a reactant. So sometimes you'll see the word heat or energy actually written into the equation. That's the third way of telling you this is an endothermic reaction. Okay. So now that I know that, let's say I come along and I increase the temperature of the environment. Okay, I make it really hot in here. Does raising the temperature sound to you like heat is being added or heat is being taken away? Correct. Heat is being added. Well, where is heat? Heat is just like one of our other reactants. If I add more of one of my reactants, which way is this going to move? Correct. It's going to move to the right. Okay. Let's try something else. Okay, this time I'm going to lower the temperature. I'm going to make it really, really cold in here. If you lower the temperature, doesn't that sound like you're taking heat away? Nod your heads. Okay, so again, where is heat? Heat is one of my reactants. If I'm taking some away, I'm removing one of my reactants. This is going to shift to the, you got it, it's going to shift to the left. Okay? Alright, so what if the reaction is an endo? Then it must be exothermic. Right? This prefix, X, we've talked about this before, that means out of. And exothermic, opposite of endo, means heat or energy is produced, released. Okay? And again, I could show this, I could tell you that this is exothermic in one of three ways. I could either just flat out say this is an exothermic reaction. I could give you a delta H value. Please notice that it is negative this time. Or we could write the word heat or energy right into the equation. All right? Heat produced, heat released. Where do you think I should write the word heat? Correct. Product side. Okay, so again, let's say I decrease the temperature of this particular reaction. Decreasing the temperature, you guys said, is like taking heat away. So which way will this shift? To the right. Okay. All right, so the point is, you can't answer these temperature Le Chatelier questions unless you know whether a reaction is endo or exothermic. Okay? And let me just give you a real world example, okay, a real life application here. Let's say that you are a factory owner, and your factory, the entire purpose of your factory is to manufacture sulfuric acid. That's all you do all day. The synthesis of sulfuric acid is actually an exothermic reaction. I'm not making that up. It is. So think about this for a second. If you are the factory owner, does it make more sense to keep your factory at a low cold temperature, a hot temperature, or room temperature? Okay, so cold, hot, room temperature, what's going to make more sense? Now, before you answer, keep in mind, you're the factory owner. Your job is to make as much of your product as possible. So think about that for a second. What do you think? Okay, yes. Keep it cold. I mean, this is exact situation. A lower temperature is going to be constantly removing heat, which is going to constantly keep this reaction moving in the forward direction, which is what you want because you're trying to make as much product as possible. All right, and let's continue with this whole business owner perspective. If your sulfuric acid plant, it makes sense to carry this out at a low temperature, would it make sense to you as a business owner to build your factory in, say, Brazil, where the equator runs through that country? No. Okay, so that's just, you know, a real life application there. Okay, so we've seen changing the concentration, that's one way to upset an equilibrium. Changing the temperature, your third is changing the pressure. Okay, don't write all of this down. Let's jump right to an example here. Okay, let's look at that first reaction. Okay, and let's say to this nice, happy little equilibrium system, I decide I'm going to raise the pressure of the environment. All right, well, listen really carefully to what I say here. If you raise the pressure of a system at equilibrium, the reaction will shift in the direction, it will shift toward the side with fewer moles of gas. Well, how are you supposed to know how many moles of gas there are? I didn't give you any numbers. Thank you. It's based on the coefficients. Alright, so on the right-hand side, how many moles of gas do I have? Correct. And on the left-hand side, I've got, very good. Okay, so in this situation, I raise the pressure. This is going to shift to, very good, to the right. All right, let's look at the second one. How many moles of gas on the left? Good. And on the right? Okay, so equal moles. Equal moles, what does that mean? No effect. Yeah. No effect. No change. Okay, last one. How many moles of gas are on the left? You sure it's 7? Pay attention. It's not 7, it's 6. Very good. How many on the right? 0. Okay, so this is going to shift to the right. Very good. Okay, so if raising the pressure causes it to shift to the side with fewer moles of gas, lowering the pressure should move it to the side with, correct, more moles of gas. Okay, and I've got this sort of cute way of remembering this. Okay, it's not all that cute. Most of you in here are juniors. Okay, would you agree that junior year is a bit of a stressful year? Okay, yeah, I would agree. And even seniors, first semester senior year, pretty stressful as well. Would you all say that everybody in this room is under, you know, a good amount of stress of some kind? Would you agree that you're under high pressure? Yes. Okay. Well, you may be different, but if you increase the pressure, like you feel like you are under a lot of stress, a lot of pressure is on you. Me personally, I'm an introverted person, believe it or not. I do not like to be around big crowds of people. Okay, I prefer to be around fewer people. All right? But let's say the opposite, okay? Let's say it's summertime, all right? Summertime, you're not in school, you're not feeling the stress, you're under low pressure, okay? Sometimes I feel so happy that I want to invite everybody I know over to my house, okay? When I'm feeling low pressure on me, I want to be around more people, okay? More moles of gas. This is what I'm trying to explain, okay? That may not help you, I don't know. It helps me. Okay, now I'm going to throw you a curveball here. What if I do this? Okay, this time I increase the volume. Well, what effect is that going to have? Very good. Increase the volume, it's going to decrease the pressure. Isn't that Boyle's law? Okay, so if you decrease the pressure, which side is it going to go to? Yeah, more moles. Okay, so just to sum up, 3 ways to alter an equilibrium. Change the concentration, change the amounts, change the temperature, change the pressure. Okay, the only other thing you could possibly see is addition of something called an inert gas. Okay, the word inert basically means like harmless, has no effect. All right, this is what that might look like. So let's say to this equilibrium system, I just decide for whatever reason to add some neon gas, you know, just for kicks, because I feel like it. Right? If you have this situation, right, and you add an inert gas, it's not a part of the reaction, it's not going to have any effect. Right? So addition of an inert gas, doesn't matter if it's on reactants or product side, no effect. The other thing you could possibly see is addition of a catalyst. And let's remember from Chem 1, a catalyst does nothing more than speed up a reaction, right? Well, a catalyst is also not going to affect your equilibrium. Okay, so inert gases, catalysts, not going to affect anything. So guys, that is it.